Hi there. Have you ever tried to predict something based on patterns? Like guessing a house's price from its size? Today, we're diving into linear regression, one of the simplest and most important concepts in statistics and machine learning. It's not just about making predictions, it's about understanding how change in one thing affects or changes other. Linear regression helps us find relationships between variables, and then we can use that relationship to make better decisions or predictions. Let's dive in. Imagine you have some data, like the size of houses and their prices. You want to answer, can the size of a house help me predict its price? Linear regression is a technique that helps us find a relationship between two things, or in technical terms, variables. The aim of linear regression is to understand how one variable affects another, like understanding how house size affects price. Make predictions based on that understanding, like predicting the price of a house given its size. For example, if you know the size of a house, linear regression helps you estimate its price by using data that shows how house size and price are connected. Linear regression is perfect for straight-line relationships. But what if the relationship is more complex, like a curve? In those cases, we use polynomial regression or logistic regression for more advanced patterns. Before we dive deeper, let's meet the three main characters in this story. Independent variable, x. This is the factor we control or know in advance. It's like the input or cause. For example, the size of a house when predicting its price. Think of it as the thing you believe affects other. Dependent variable, y. This is what you're trying to predict or understand. It's the result or effect. For example, the house price depends on its size. It's the thing that changes because of the independent variable. Continuous values. Linear regression works best with variables that have continuous values, numbers that can take any value within a range. Continuous values mean you're working with numbers that aren't fixed into categories like small or large. The goal of linear regression is to draw a straight line that best fits the data, also known as line of best fit. Which implies that the error between the predicted and actual values should be kept to a minimum. This line shows the relationship between the independent variable x and the dependent variable y. The equation for this line is y equals mx plus b. Y is the value we want to predict, like house price. X is the known input, like house size. M is the slope, how steep the line is. It tells us how much y changes when x changes. B is the intercept, where the line starts on the y-axis when x is 0. Let's say, for every extra square foot of size, the house price increases by $200. The starting price for a house, at 0 size, is $100,000. The equation becomes price equals 200 times size plus 100,000. If the house is 1,500 square feet, the price is 200 times 1,500 plus 100,000 is equal to 400,000. To find the best line, linear regression minimizes something called the error. This is the gap between the actual data points and the predictions made by the line, also technically called residual. Now, to find the best line, the model uses a process called gradient descent. Imagine you're standing at the top of a hill, and your goal is to reach the lowest point. The idea is to take small steps in the direction of the slope to gradually get to the bottom. That's what gradient descent does. It adjusts the slope and intercept step by step to reduce the error and find the best fit for the data. Linear regression is everywhere around us. Here are some examples. Real estate, house price, y, depends on size, location, and number of bedrooms, x. Business, sales, y, depend on advertising budget, x. Health, weight, y, depends on height or age, x. Weather, temperature, y, depends on time of day or season, x. Let's quickly see how to implement linear regression in Python. Here's some code to predict house prices. And that's how you use linear regression to make predictions. While linear regression is powerful, it does have some limitations. Limited to linear relationships, it works best for data that shows a straight line relationship. If the data is more complex, linear regression may not work well. Sensitive to outliers, extreme data points can affect the accuracy of the model. But here's the solution. For nonlinear relationships, you can use more advanced models like polynomial regression or support vector machines. For outliers, techniques like ridge regression or lasso regression can help by adding a penalty for large weights, making the model more robust. By understanding these limitations, we can choose the right tools and improve our predictions. I hope linear regression feels much simpler now.